All right, welcome back to the second half of Monday's lecture. It is being recorded on Monday, which makes it a Monday lecture. Praise the Lord. So we're picking up where we left off at the Wittig reaction. And this is something I really wish I was doing this in person with you, because there is such a thing as a Wittig reaction dance that kind of explains the mechanism for this, which probably means that we'll actually have to do that on Friday in person, just to revisit this reaction. But Wittig reaction, I hope you're excited about it, not just because of the Wittig dance that can explain the mechanism for this, but because it's a really useful reaction to form an olefin from carbonyls. So, but before we get into that, I just want to talk about how to prepare the Wittig reagent. It's kind of like before we talked about Grignard reaction, we had to talk about how to make Grignard reagent. So let's talk about that. So the ingredients for that, really three things, not all at the same time though. You need a triphenylphosphine, which is this thing, which is something that you definitely want to know the structure of. It's triphenylphosphine. In the literature or in the textbook, often abbreviated like so. So just be aware of that. And then you also need, so that's sort of first ingredient, you also need an alkyl halide. This is 2 alkyl halide. Okay, because the phosphine has to do an SN2 reaction. Okay, so this is happens, and some of you might be surprised that happens, because that phosphorus may look so bulky that it shouldn't be nucleophilic, right? But remember that to have nucleophilicity, it's not just about bulk, but polarizability. If you're very polarizable, you make a good nucleophile, right? So that was a criteria. And phosphorus, compared to things like nitrogen or oxygen, which are only second row elements, phosphorus being in the third row element, it's a really big and polarizable atom, and so it's actually very nucleophilic, even when it has bulky things like phenyl group. And also I want to point out that these phosphorus carbon bonds right here are actually pretty long, because phosphorus is a big atom. So these phenyl groups, they look bulky, but they really are kind of far away from phosphorus. So SN2 reaction is very much possible, and after which you end up with this salt, which is this salt between phosphonium ion and the halide, and to that you would add the third ingredient, which is the strong base. Okay. Okay. Once you add the strong base, though, you of course it's gonna take a proton that's somewhat acidic in this whole mixture, but which one is it going to be? That's the big question, right? And there's really not many to choose from. I want you to know that, like, the hydrogens on the phenyl groups, they're not gonna be a good candidate for it, okay? But and this hydrogen here is not gonna be a good candidate either. There's nothing to stabilize the negative charge, but the hydrogen right next to, we would say alpha to the phosphorus, that would be a pretty good candidate. And the reason for that is once that gets deprotonated and you get the conjugate base, you get, I'm gonna abbreviate the phenyl groups. You get this weird species that has both a negative ion and a positive ion next to each other. And there's a word for such weird situation, and it's called ylid. And I want you to notice the kind of resonance that this could have. In you notice you essentially have phosphorus carbon double bond, and this is what we would call a Wittig reagent. And I want to point out, just so that I can spare you from sounding like amateur, like student, right? Oftentimes people mispronounce this like Wittig reagent. This is a German name, so the W is pronounced as a V. You can complain to what's her name, Angela Marco or something like that. I think she's the chancellor still, about the German language, not to me. And also sometimes for some reason people add an N to this name and call it Wittig reagent, but that's not a thing either. It's Wittig reagent, okay? Although I think to be technical about German pronunciation, I think you're supposed to pronounce it like Wittig or something, but you know, it's been too many years since I learned German, so we'll just call it Wittig reagent. So the key idea here is you have phosphorus carbon double bond. All right, so how do you use it? Okay, let's think about a situation. You start out with bromomethane, and then you treat that with triphenylphosphine to do that SN2 reaction, and then maybe you put in potassium t-butoxide, and you would end up with this Wittig reagent. Hopefully that makes sense, and that's something I would encourage you to maybe work out the mechanism for. Let's think about another example of a Wittig reagent. You can start this off with like a secondary halide as well, just not a tertiary. Oops. Not a tertiary halide, but secondary is okay. So in this case, I might still have to treat it with triphenylphosphine. The strong base, sometimes you might see other choices like N-butyl lithium, which is a very strong base, because if you think about it, this is the structure of N-butyl lithium. There's a carbon metal bond, and of course all the charges on the carbons. It's basically a carbanion, and that's one of those, such a strong reagent that it's really scary, and it's very pyrophoric. If you squirt this into the air, it'll combust spontaneously. But so it's that strong of a base, so it's no wonder it could make a Wittig reagent, and that's what you would get. Okay, so hopefully you're okay with the Wittig reagent generation. And with that, let's actually talk about the fun part, which is the Wittig reaction. So this ethyl Wittig is the reagent that we just made a moment ago. And what if we treat that with an aldehyde? What do you get? Maybe I'm gonna show you the product first in this one. You actually end up with this cis alkene. If trans and cis matters, then it actually goes for the cis geometry, which we'll briefly discuss in the mechanism. So how does this work? Remember that the way that most carbonyl reactions work is through nucleophilic addition. I hope this won't make you dizzy, sorry. It's actually kind of making me dizzy, so it probably is doing that. Oh, where'd it go? Dude, there you go. All right, let me... Okay, I can get this together. I'm a professional, and I'm an adult. Okay, so so here's a nucleophilic addition like pattern that we talked about, right? So it's always nucleophile adding to the carbonyl, and it's gonna be the same story even with the Wittig reaction mechanism. And you might wonder, what is the nucleophile? Remember that this carbon in the other resonance form, I guess maybe I'll just draw the resonance, might as well, has a negative charge on it. Although that to say, this carbon has a really strong partial negative charge, so it's very nucleophilic. But I want you to notice how I'm technically using the pi electrons that is kind of understood to be pretty much here in the resonance. So I'm using that to attack the carbonyl. Of course, the electrons get kicked up to the oxygen. So this is a nucleophilic addition step, and you might wonder, did I actually draw that irreversible error on purpose? And then I did, because remember when we talked about reversibility last semester, every time you make like a new carbon-carbon bond or carbon-hydrogen bonds, usually those are very irreversible. So as a result of this, you would end up with this intermediate. Okay, and this weird intermediate that has a alkoxide and a phosphonium cation in the same molecule, there's a word for that too, it's called betaine. And where we're going with this, I don't know if you guys remember the sort of so-and-so has a crush on so-and-so gossip among the elements on the periodic table. Phosphorus loves oxygen, so I'll just write this again. Oh, that's a horrible heart mark, but symbol, but you guys get the gist of it. So this is a great opportunity, don't you think, for the two? I mean, this is one of those scenes in like in the movie when you're watching like I can't remember the last time I actually watched a chick flick. But you know what I'm talking about, like an obvious setup that these two are going to get together, right? Because oxygen and phosphorus, on top of it, oxygen has a negative charge, phosphorus has a positive charge. I mean, if the two aren't meant to be at this point, who are, right? So this happens, and then you end up with, this is kind of like one of those odd couples, okay? I mean, like once they're together, they look a little odd, because that's like a four-membered ring and stuff. If you recall, the four-membered ring that looks like this with ether is called oxetane. Likewise, this intermediate that is a four-membered ring that has an oxygen and a phosphorus in it is called an oxophosphatane. Okay. Now, it is somewhat stable, but not too stable. It won't last like this forever. And remember, oxygen and phosphorus, they love each other and want to maybe have like an exclusive relationship, not involving those two pesky carbons. So there's a solution to this. You just have to do the opposite of cycle addition to like cleave off the carbons. So in other words, we want to form this double bond between oxygen and phosphorus so they can be forever together. And I mean, they're going to be forever together. I'll mention that in a minute. And then that would, to prevent carbocations or anything like that from forming, you need to rid of those two electrons off of phosphorus and then onto the two carbons, which will, of course, create the double bond. Oops, wrong color. So that would be the alkene product. And I kind of technically glossed over the reason why you end up with a cis geometry from this, and that has to do with the way that the Wittig ylid approaches the aldehyde, and it just so happens that these two alkyl groups end up being cis at this juncture, like that, or on the same side. But that stereochemistry is a little bit hard to explain at the level that we're trying to understand organic chemistry. So we would have to defer something like that to like advanced organic chemistry and whatnot. But I do want you to know what the byproduct is, though. That's the result of phosphorus and oxygen being together with the double bond. And this is like a brick dust, and I mean it's like so stable like brick dust because oxygen and phosphorus are together, and also it's a horrible thing. It has kind of a bad solubility issues, and in synthesis often this is really hard to get rid of, so I really hate this stuff. But if you ask any synthetic chemist, professional chemist, they'll tell you how much they hate triphenylphosphine oxide. It's kind of like some of those people that show like a little too much PDA in public that you don't want to be around. It's kind of triphenylphosphine oxide is. There's actually even papers published just on how to get rid of it because it's so annoying. But that's the other product. Okay, so this would be a great time to pause perhaps this video, even though you might miss me talking. But you might want to actually take a look at these two synthesis examples and see if you could come up with the syntheses that, well, the hint is, of course, that you're going to probably have to involve Wittig reactions. So pause the video, because it would be awkward for me to just be silent in a video for a minute. So assuming you actually thought about this, one thing I want you to kind of take away from this is that Wittig reaction is kind of like the opposite of ozonolysis. As far as the result goes, the mechanism is nothing like, but what does that mean? That means, remember, ozonolysis would cut up an alkene and make a carbonyl compound, right? Like if I were to do ozonolysis on this, I know this is not the right way to think about synthesis, but let me indulge with me for a sec. You could end up with this dialdehyde, right, through ozonolysis. But we want to do the opposite of that. We want to actually make this dialkene from like a dialdehyde like this. So we need to do the opposite, right? And whenever you need to do the opposite of ozonolysis, you can use the Wittig reaction. I hope that makes sense. So we're going to use two equivalents of this methylene Wittig. I don't know if you recall from our discussion about NMR, the word methylene refers to CH2 group. CH3 is methyl, CH2 is methylene, CH is methine, if you recall. Now, how do you make this aldehyde? Well, we probably could make that from ozonolysis from this starting alkene, because ozonolysis would cut up that, I should do that in the middle, alkene in the middle, and you create two aldehydes, right, with reductive workup in the end. So that would complete the synthesis. So hopefully that makes sense to you. All right, the second problem, how do we do that one? This one maybe looks kind of hard, and assuming though that we need to make one of those double bonds present in the product here from Wittig reaction, there's two options, like should we make this from Wittig or that from Wittig? And as you can imagine, if you go through the mechanism, it would be hard to do intramolecular Wittig, which means it's hard to make a cycle using Wittig reactions. Okay, so what we're going to do instead is we're gonna make this double bond via Wittig. Okay, so once we kind of decide on that, the aldehyde, or I just, so far we've only used aldehydes. I want you to know that Wittig also works with ketones, but I just don't have such examples shown here at the moment. But the carbonyl compound that would produce that would be this aldehyde. Hopefully that makes sense. And the Wittig reagent that would be necessary, sorry, that's kind of squished, would be the cyclopentenyl cyclopentyl Wittig, which can be produced from this cyclopropyl bromide and treatment with triphenylphosphine, perhaps N-butyllithium would give us that. And how do you make this aldehyde that we synthesized? Now, I want you to notice that this aldehyde, I'm talking about this molecule, has cyclohexene embedded in it. And hopefully you guys remember, every time you see cyclohexene, that's a signature of, hopefully you guessed it right, Diels-Alder reaction. So we could start from here and get to that. We do have a diene as a study material. So of course the other partner has to be a dienophile. And dienophile, as you recall, has to have an electron withdrawing group like this, and like some heat. So that would give us a Diels-Alder product, and that would complete the synthesis. So hopefully you guys were okay with that one. And with that out of the way, here's our last reaction we want to learn in this chapter. And this one, we probably won't spend too much time, partly because of the time we have left, but also, yeah, it's just one of those topics that we just don't have time to put too much emphasis on it. But in real life, this is kind of a synthetically fairly useful reaction. And what Baeyer-Villager reaction does is to introduce an oxygen to a ketone. So we could introduce oxygen either here or there, and then turn that into an ester. That's what it's able to do. So as you can imagine, that's a really useful synthetic method, because you actually literally can break a carbon-carbon bond and have a totally different carbon skeleton and then insert an oxygen in the process. And to do this, you need reagent that looks like this, and then hopefully you remember what that functional group is with 3 oxygens, or seemingly one too many oxygen. Remember, that's called peroxy carboxylic acid, or colloquially also known as peracid. And that's what's needed. And in the past, we've talked about examples like these of peroxy acids. Those are important examples. Okay, so how does this work? Let's think about the mechanism, and then think about what products exactly we would get. Like the name suggests, peroxy carboxylic acid is somewhat acidic. It's not as acidic as carboxylic acid, but because of its a look of like a tiny bit of acidity, we could imagine that this happens to some extent, not to a large extent, but it could happen. And once it happens, you would end up with this activated carbonyl. Once it's activated, right, even like weak nucleophile could attack, and this negatively charged oxygen is a pretty good nucleophile. In fact, peroxide is a pretty good nucleophile, so this would not even hesitate for a minute to add to that. It's a nucleophilic addition step. And we would end up with this intermediate. Now, I'm going to draw this a little differently, just so that the next step can be drawn a little more easily. Because it's kind of one of those, like a cyclic type of a mechanism. And looking at this, I want you to notice or remember how oxygen-oxygen single bond is a very weak bond. It's notoriously weak and unstable. And so for that reason, it will want to break. Now, if this is going to break, which way would the reactions go towards? I want you to think between this carbon and that carbon, which is more electron withdrawing? And of course, the answer is the one with carbonyl, right? So the electrons here will flow towards the carbonyl, like so. And that will, of course, kick up the electrons to the oxygen. So instead of it not being with a negative charge, you could grab this proton right here. And if that's going to grab the proton, these electrons have to go somewhere, and they might as well come down to form an oxygen-carbon double bond, which is a pretty strong bond. But then you might notice that at this carbon here, we're going to have total of 5 bonds, and then you can't have that, right? So you're going to have to shift something. And you might also notice how at this moment, this oxygen here would end up with a positive charge, and you can't easily have a positively charged oxygen. That would not be good. This would be very partially positive right now. So what's going to happen? It's going to be the same situation as when we have to deal with a carbocation that's very unstable because of electron deficiency. Remember, carbocations are prone to alkyl shifts or hydride shifts. This intermediate could do the same thing. This is a 1,2 alkyl shift. So this right here is 1,2 alkyl shift is what's going on there. And once that happens, I want you to follow the arrows. Remember, we were saying that there's going to be carbon-oxygen double bond, and that this carbonyl carbon is still attached to that oxygen, and that ethyl group migrated to the oxygen. So we have this ester, right? And then what happened to the peroxy acid? Well, it ended up being acetic acid, which is abbreviated like so. And this is the product. Now, there's a question still here that needs to be answered, and that's which alkyl group should migrate, okay? Would it be the methyl group that migrate or ethyl group that migrate? And that's what we meant by the migratory aptitude up here. Basically, the rule of thumb is it's the more electron-rich group that migrates. And that makes sense because in this migration step here, right, which alkyl shift is so that we're trying to quench an electron deficient oxygen's thirst for electrons, essentially. So it makes sense that it's the more electron-rich group that migrates. So if you compare between methyl group and ethyl group, of course, ethyl group is more electron-rich, so that's the one that migrates instead of the methyl group. Okay. Hopefully that makes sense. And then, let's see, ethyl. Right here is more electron-rich. Than methyl. Okay. Oh man, I didn't leave myself much space there. So with that said, about the mechanism, I guess I should probably draw the product. I don't know how that turned out. That looks a little better. And then acetic acid was the byproduct, right? You might want to pause the video for a second just to see if you can come up with the product for these two last examples we have here. So pause the video, and even better, see if you can figure out the mechanism. Okay, So the product here is going to be, the main question though is going to be, is it going to be this alkyl group that migrates or this alkyl group that migrates? And between the two, the carbon on the left being tertiary, that's gonna be more electron rich. So that's the one that migrates. And I want you to know that that migration happens without some sort of inversion like SN2. So the ester that we're gonna get is gonna be this product, okay, without any inversion of the stereochemistry. What about the other ketone here in the last example? We're comparing between this carbon, which is quaternary, and this carbon, which is secondary. So hopefully it makes sense to you that it's going to be the quaternary carbon that migrates. And so for that reason, we're going to see the oxygen inserted here, okay? So the product is going to be, maybe I'll just draw it over here. Like so. Okay. And I'll try to provide a time that you could ask questions, hopefully soon, maybe on Wednesday. So if you have questions, please let me know if any of this didn't make sense or you want me to go over something again. But these last two examples, I would really highly encourage you to go through the mechanisms yourself so that it makes more sense to you. And that'll be a good practice. So that is it for chapter 19. I'll see you guys in the videos for chapter 20, which for now, the next exam, it's gonna just have chapter 9 up to only chapter 19. So see you guys.